Right, hi all. This is a small correction to the end of the video I did for you. So the modelling was all correct. I've just gone back and worked out why we didn't get the right values, and I've made one very, very small mistake which threw everything out. So I'm just going to show you how to do the FEA again. Okay, so we've drawn our cylinder, or a quarter of our cylinder. We're going to do a study, so we go to simulation. We're going to do a new study. I'm going to call this pressure FEA. It's a static study of pressure FEA. Give a tick. All our options will appear. Okay, so we need to, as we said last time, we need to fix 3 of these faces. So we roll the slider fixtures. This is so that there is a little bit of movement, allowing it to effectively expand, but it's not moving in space. That's why we use a roller slider rather than a fixed geometry. Okay, so again, the face opposite our split line and the 2 rectangular faces, we fix them in space. Click OK. Add an internal load, pressure on that internal face there, and that was our pressure of 6.5 meganewtons, 6.5 times 10 to the 6. Okay, and just with that round, we also had a pressure on that face there of 100 kilonewtons. So there's our pressures, all our fixtures. We can now run this study. Now, what I've found with doing this, whether it's across the remote desktop or whatever, I can't increase the mesh on the whole cylinder without it throwing me errors. So I'm just going to run the study on the default mesh. And while that's meshing, we'll just look at the theory of what we're trying to show. Okay. So the theory that we're trying to show is in the Lame equations, which I have here somewhere. There we go. Okay. So we have that the radial stress is A plus B over R1 squared. Okay. Or A plus B over R squared. Okay. And that the hoop stress is further up, down. The hoop stress turns out to be A minus B over R squared. Which I can't find on here, but it is in this document somewhere. It's equation 4 and 5. Actually, there we go. So there's a theoretical stress there. Okay, our strain gauge is measuring strain. Okay, so we work in the theoretical stress, and then our model is going to give us this. Now, what's important when we're looking at the FEA, okay, is that when we do our analysis, okay, we should find that the hoop stress is always tensile, but changes throughout the radiuses, and that the radial stress is always compressive. Okay, so that's what we're looking for with our FEA. Okay, and what we should find is that those stresses fall through. What we also need to remember here is that we have 2 radiuses. Okay, so when R is R2, then the hoop stress is atmospheric pressure. So our radial stress is 0, and when R is at R1, then the radial stress is minus P, because it's a compressive stress, and that's the pressure we'll be put inside the material. So what we should find is our pressure, our radial stress, should go from basically our internal pressure up to 6.5 megapascals. Near enough. So let's have a look at that. So we've done our FEA, and we've got a nice colourful pattern, but these don't look right. Okay, and that's because we're doing a von Mises test here. So what we need to do is come in and change this. Okay, so we double click the stress, and rather than a von Mises stress, we want to make it SX, SY or SF. We don't know which one yet. We're going to put it. Now this is the bit where I made a slight error. Okay, what we need to do is find the reference plane, the reference axis, not the reference plane. That's what I did wrong. Okay, so in that advanced options, where we want to set it plane, axis or coordinate system, we need to find our reference axis and select that. Then click OK to go. And you'll see on this one, the stress in the x-axis. Now what I'd also like to do on this is just going back in there, just to take the deformed shape out as well, because there's not much deformation, but it moves the cylinder and doesn't move the arrows and things like that. So you see, you've got this nice rainbow pattern going from 6.8 gigapascals to minus 7.244 gigapascals throughout the cylinder. Okay, these are all negative. Okay. If we do the same test on the stress in the y direction, now what we should be able to do is it should still be on that axis, which it is. You'll see all these stresses are positive, with the biggest stress on the inside. So I would suggest that's the hoop stress, and the stress in the z direction it's always worth checking all three. Is pretty much linear throughout the material. So I would suggest that is the longitudinal stress. Okay, so let's go back to the radial stress. That was the first one we're going to look at, the stress in the x direction. Okay, so what we're now going to do is with the stress, we'll come back to the nice colourful one. Stress in the x direction, I'm now going to right click it and set a probe in place. Okay, on selected entities, I'm going to select the split line that I ran straight down the middle of my right. And I'm going to update my data figures. What we can also do is have a quick look at that with that plot. So if I plot that stress, you'll see our hoop stress goes from not far, our radial stress goes from not far off 6.5 gigapascals, a bit less, up to 0 gigapascals at the top end. Okay. And what we see here is, in this graph, is all of the node numbers and their values and their data. Now what it also shows us is that the x coordinate is not changing. The y coordinates are positive and negative the same magnitude. Okay. That's because we're going at 45 degrees on the axis. So I'm going to just take all of this data, okay, the value, the node, and just select all of that, okay, copy it. Now on the remote desktop, Control C and Control V might not work, so you might need to right click and click copy. Go into Excel and paste that data into Excel. Okay. Because what we're now going to do is actually these node numbers are just labels. I'm not going to do that. What I'm going to put here is a formula. So equals the square root of at squared plus at squared. i.e. I'm going to do Pythagoras on those coordinates. So you see that is at the 75 degree, at 75 mil radius. Scroll that down. So you get 18, 23, 27, 32, 37, 42, 40. Okay, so what we can then do is take that and insert a chart. Okay, because these are negative, they're compressive, and we get pretty much exactly what we're expecting to see for the radial stress. Okay, if we look at that same analysis but for the hoop stress, okay, so I'm just going to come off that probe result again, change my stress to be S in the Y direction. That gives me my hoop stress. Again, set a probe in. Pick that point. Oh, sorry, unselected entities. Pick that point. Update my data. Again, we can plot the graph and see how the hoop stress increases to there, but bear in mind that that is the internal diameter at radius, and that is the external radius, and these values, the parametric is just normalizes those values. So again, we can take those values Control Shift down, Control Shift left, click and copy, pop them into Excel again, pop them there, paste those values into Excel, and again I can just copy that formula down. So you can see how the hoop stress changes, but is always tensile. Okay, so that and those results from that FEA analysis should match up with your theoretical results for the stress at various points in the cylinder. Okay, sorry for the very slight error we did on the first video, but I hope that's fixed everything up for you, and I'll see you